Welcome to Structural Dynamics class. In this class, we will study special cases in arbitrary force. So, in the previous class, we have studied about the arbitrary force and how to find the solution for the arbitrary force, how to find the response of a single degree of freedom system for any arbitrary force. So, let us discuss the outline of this class. So, we will first discuss about the summary of how to find the response due to arbitrary force acting on a single degree of freedom system, and then next we will find out the response to a step force. Step force means if a force is applied suddenly, how the response will be, and then if the force is linearly varying, how the response will be, and if the force is pulse type, so that means suddenly applied force and then after some time that force is removed. So, these three special cases we will discuss in this class. So, first, as you know, this is a dynamic equilibrium equation. Mu double dot plus Cu dot plus Ku is equal to P. So, this dynamic equilibrium equation is equation of motion for this single degree of freedom system. So, if say P of t is sinusoidal, we have discussed this one, and if it is arbitrary, so that also we have discussed. So, how the how can we calculate the response due to arbitrary force? The procedure is that we will first try to find out the impulse at every point and then response due to each impulse. Before that, we find the response due to unit impulse. So, h t minus tau is the response due to unit impulse, and then we will multiply that with the impulse value at any point, and that will give us the response to one impulse. So, response to all such impulses is the integral of 0 to time t up to time t. So, p tau h t minus tau d tau. So, this is the convolution integral. So, if we substitute h t minus tau in this, we get for damped free vibrations and for undamped free vibrations, we will get the complete response. So, now we will make use of this one in some special cases. So, here we are discussing three special cases. So, the first special case is if a force is applied suddenly. So, let me explain you what is the meaning of that if a force is applied suddenly. So, let us take this cantilever beam, and a force is suddenly released and then it is falling suddenly on this beam at one location, or say simply supported beam, and force is suddenly applied on this one, or on slab force is suddenly applied. So, now how do we calculate this one? So, as you can see in this graph, at t is equal to 0, force is suddenly applied and this force is continuously there on the system. So, how the system is going to respond? Okay. So, intuitively if you look at this one, if force is suddenly applied, what happens is because of this it will come and vibrate, oscillate, and then after that what is going to happen, because force is not going to be removed, we are not removing that force is still there. So, how the dynamics will be of this member, or say simply supported beam and force is suddenly applied, how it will be, or say on a slab if we suddenly apply a force, how slab will vibrate. So, that is what we are trying to understand. So, force function Pt, which is constant. So, continuously at any point of time P0 is there. So, constant, that is fixed force is there on the system. So, then let us find out response to undamped system. So, if it is undamped system, we know that ut is equal to 1 by m omega n integral 0 to t p tau sin omega n t minus tau d tau. So, for that p tau, so you can see this at any point of time p tau value is p0. So, if you replace that p tau value with p0 and then rest of the thing remains same. So, now we can evaluate this term. So, if you integrate this term, so p naught will be constant, it comes out sin omega n t minus tau into multiply by d tau. If you integrate it and expand and solve, then apply the limits, then we get 1 minus cos omega n t into p minus k. So, what is this p minus k? P minus k is the static deflection UST, something like at rest condition. When force is acting on the body at rest, then P naught by k, that is a deflection. So for cantilever beam, if I take say cantilever beam, if P naught force is acting, P force is acting, so what is the deflection of that cantilever beam? We already know that P0 L cube by 3 EI. So when force is applied at the free end P0, so deflection will be P0 L cube by 3 EI. This is the deflection. So exactly this, like P0 by 3 EI by L cube. So this K means this value. So K is the stiffness of the cantilever beam. So that is the static deflection part. Multiply by 1 minus cos omega nt, this is the dynamic part. Now if we plot this response, it looks like this. So force, like as an example problem, a force of 100 kilonewton is acting, so 100 is continuously there. Then what is happening is the displacement value, which is 0 at the time t is equal to 0, because of the application of the force, suddenly it has increased. Okay, so if we take say undamped vibration, suddenly it has increased and then continuously it is oscillating there. Oscillation part is coming from this one. As you can see this one, if you look at this, so the maximum value of this one, maximum value of this function, so if we take one differentiation, say du tau t by dt, if we take, so the maximum value of this, so if we make this equal to 0, so then what we get from this is at regular intervals it will become maximum, minimum, maximum, minimum, maximum, minimum. So if we substitute this value in the time at this location, so we get this as minus of -1, so that means 2. So static deflection, twice the static deflection is the maximum value of displacement. And then if I look at this one, you can see this one, this 5 is the P naught by K, that is static deflection value. So as we can write like that also, this is P naught by K and this value will be 2 P naught by K. So this is oscillating, so green one, undamped system continuously it oscillates about the mean position. Mean position is static deflection. Now if we provide damping in the system, so which is blue curve, so you can see this one, after few cycles vibration amplitude reduced and it merged with the, it comes to rest at the static deflection value. So if we understand this phenomenon, okay, it's a cantilever beam and then load is applied here. So because of the application of the load, it comes here and vibrates and then finally becomes at rest condition. So at rest condition, this continuously it goes as a static deflection. Before that, it's a amplitude is there, double amplitude is there, then slowly it vibrates few cycles and then comes to rest. So at rest condition is in case of suddenly applied force is P naught by K, and the minimum and maximum values will be, minimum value will be 0, maximum value will be double of P naught by K. So that is a response of a step function. Now let us consider another special case, which is linearly varying force. So here force is not all of a sudden, here force is acting gradually, force is being increased gradually, step by step like that, step by step. So it is something like, so there is a member on which say I am putting 1 kilonewton load and then another kilonewton load and then another kilonewton load, another kilonewton load. So it is increasing gradually, it is increasing gradually. So when force is increasing gradually, how do we find the response to that? So again using the same principles. So this function Pt is P0, which is the amplitude, the final value, into T by Tr. Tr is the time up to which this ramp, it is ramping up to that point, Tr. So when time t is equal to 0, P is equal to 0 from this function. When time t is equal to Tr, it is attaining its full value. So if we take this as a force and apply into the our Duhamel's integral or the convolutional integral, how this solution will be. Let us look at that. Response of undamped systems. So 1 by m omega n integral p tau sin omega n t minus tau d tau. If we look at this one, response, and then substitute in the place of P force value. So this function. So P by TR, T is now tau here, sin omega t into T minus tau d tau. So the response of that will be P naught by K, T by TR minus sin omega n t by omega n into TR. So the function, the response or displacement value will be something like this. Okay, undamped system is a blue line, damped system is a green line. Actually, if we use say another value of as an example, so how it looks like is, so it is something like this. It merges in that. So this is response to linearly increasing force. Now let us discuss another special case, that is of pulse force. So pulse force is this one. So as you can see in this plot, so this force is applied to some extent, till some extent. So let's take say this is TR, and after that it stops. So force is, say for example, suddenly force is dropped at time t is equal to 0, amplitude of force is P0, and it is applied for say few seconds and then removed again. So what will happen due to the application of this force? So force function is P is equal to P0 at time t is equal to less than or equal to Td. So this is Td, and Pt is equal to 0 when t is greater than Td. So that means after this one it is 0. So its force is something like this. So suddenly it is increasing to P0 and then till Td, and then it comes down, and after that it is 0. This red one is force. So again we come to response to undamped systems. As you can see in this one, there are two things. One is up to Td, and then the second component is starts from Td. So P tau sin omega n t minus tau d tau, and P tau sin omega n t minus tau d tau. So this is from Td up to any time, and here the time is between 0 to Td. So two functions are there. So in between t and Td, so any time value less than, say if this is say 2 seconds, less than 2 seconds, this value is holds good, and then beyond that this value holds good. So we need to consider one important thing in this one, that is at t is equal to Td, so this second function starts. So in that the initial displacement term also will be there, that is u Td will be there, cos omega n t minus Td, u dot Td divided by omega n sin omega n t minus Td. So that will be there. So this is after Td. So this one is before Td. So before Td is this function, after Td is the second function. The same problem can be understood in a different manner. So that is the same thing, we can continue it like this. Say if a force is acting continuously from here forever, and then the second one is force is acting in the negative direction from Td, like this. So this is Td. So what this gives is the constant impulse value. So P naught, okay, a step force, response due to step force from time t is equal to 0 continuously up to any point of time, and this function gives response to step force from time t is equal to Td. If we subtract this from this one, then also we get the same value. So how does this response look like? So you can see this one, suddenly when force is applied, so vibration amplitude which starts from 0, and this is P naught by K, static deflection part, suddenly it increases and then it is oscillating. So let's look at first the blue line, and then at this point suddenly force is removed. So when force is removed, so whatever is initial displacement, that is u at Td d and then u dot at Td will become initial conditions for free vibrations starting from this point. So that's how you can see this, that is initial conditions for free vibration. Okay, and then if we look at say damped free vibrations, so you can see the the red line. So because of damping it came to rest, almost the total energy is removed from the system, and suddenly after this one we are removing the load. So when we remove load again, because of that oscillations will take place and then finally comes to 0. So here it is not coming to 0 line, it is coming to static equilibrium position, and here it is coming to equilibrium position where force is not there. So 0 displacement condition. Here static equilibrium, but equilibrium condition is met with at P0 by K. So that is static deflection. Here it is 0 because force is completely removed, here it is 0. So these three important cases we have studied. So in summary, in arbitrary force case, so first we have understood how the response to arbitrary force can be computed by dividing the force into a series of impulses and then find the response due to unit impulse, multiply by the impulse, and then sum all the responses to get the total response. And then we have applied that to three special cases, that is step force, second one is linearly varying force, and third one is pulse force. So these three forces special cases we have studied in this class.